So, like I mentioned, the last thing we have to do is do code conversion. So, I guess we'll get a little bit of a schematic of this. So we'd like to think about this as input and then an encoder, because we would like to be able to use a device that we don't have to input in binary. So we'd like to input probably in base 10 or even character form, and then we'd have an encoder. Then we'd have some processing. And we could have, at this point, it could go on to decoding it. And then output. I guess if we wanted to be complete here, we might have storage in here. So something like that. So I'm going to talk a little bit about encoding. How can I convert decimal into binary? And then about decoding. How can I convert binary back into an output? Maybe have a 1 through 10 LEDs light up, and then we'll talk about trying to drive a 7-segment display. You get a little practice on that in lab also. So let's talk about encoding first. So with an encoder, a fairly common encoder would be like a 74147. I think your text talks about that, and it has 0 through 9 inputs. See how close I got. 0, 1, 2, 3. So those would be your inputs, and then your outputs would be your binaries, the A's, B's, C's, or D's. And the bubbles simply indicate that it's activated with a low. So if I looked at a truth table on this, our inputs would be 1, or I guess would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then our outputs be like that. So if all of these are high, it's going to activate on the first low. So if all of these are high, all of these would be high, indicating a 0. I guess we wouldn't necessarily have this one, but we'll take this off because that would be, okay. So then if I have a high, a high there, then a low and a high and a high and a high. We're trying to get to 6 then, right? So it'll be a high, a low, and a high would be how that works. And we'll see some of these activates on high, some of them activate on low, depending, like when we go to the 7 segments, just whether you have a common cathode or a common anode, depending on which way you would want it to be. So that allows you to convert from base 10 into base 2. That's hopefully fairly straightforward. I think you're asked to build one of these in lab, not necessarily a 4-bit, but a 2-bit. So let's look at what that would look like. Yes.
How does the 4 output represent the base 2?
Here?
Yeah. How does that represent base 2?
Well, you have the 2s, I mean the 1s, the 2s, the 4s, and the 8s. Yeah. So let's try this. We'll go on to a decoder then. And so let's try a 2-bit. So this is going to be fairly small. BCD to decimal. Okay. And I'll put a circuit up here and we'll see how this works. We'll see if we can come up with a truth table for it. We'll use some NANDs. And we'll have our B here. And then A. So invert A and go up into there. And into here. B, what do I want to do in there? The last one is a B. We'll say that this is our 0, our 1, our 2, and our 3. So those are all outputs. So let's look at the truth table on this. If I have an input for the A and the B, and then we'll look at 0, 1, 2, 3 as our outputs. So there's in and out. So if I have a low on A and a low on B, what am I going to come up with? So we're going to end up, if I have a low here, I will get a 1, right? And if I have a low here, I will get a 1 there. If I have a NAND with 1, an AND with 1 would give me 1 and 1 would give me a 1, but a NAND should give me a low, shouldn't it? So I'll have a low there. And then it doesn't take, we can go on to the next one here, but it doesn't take much to recognize you would have a 1 here, and then you would have a 0 there. So you're going to get a high out of this thing. And you could go on and you'll have something like that. So we'd get 0 out of that. If I take a low and a high, what are we going to get out of this thing? So A is low, so I have this inverted, so that's a 1 and a 1. And then B is a high, so this would be a 0, so we'd get a high out on this. What would the next one be? With A being a low, this would be a 1, and B being a high, you'd have a 1 there, wouldn't you? So you would get a low. And if you kept going down the circuit, you'd get a high and a high. So that would be our 1. And I'm not going to go through each one of these, but if you have a high and a low, then you would get a high, high, low, high. And if you have a high and a high, you would get a high, 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 and a low. So you've really got a 2-bit, you're going from binary, a 2-bit binary number A and B, to a decimal output. And you could do a 4-bit. You're just going to have a lot more gates there. So this is actually one of the things that you're going to be building this week in laboratory. One thing that's probably a little confusing here is that it's activating on the low, and sometimes they do that depending on whether you want to turn something on or off or how your logic is arranged. Questions with that? And I think on the website it has a circuit diagram for this to help you with Lab 7.
So high is 0 and low is 1.
A high would be 1 and a low would be 0. So all of your lights would be on here except for this one that would be off. So high is 1, low is 0.
So an L going into the input, a low going into the input, 0, 0.
Right. So they have these, I mean, if we look at a 7442, you can get these packaged. Basically, the logic that you're going to have here is your A's, B's, C's, D's for the 1s and the 2s and the 4s and the 8s. And then you'll output this particular one is you're going to have 0. Something like that. It'll activate with a low. But you know, we're not going to use this one necessarily in lab because when we put in a, let's say, a 4-bit number, I don't know that we want to turn the LED 5 on or off. I mean, we'd probably like something a little easier to read. So that'll take us to a decoder driver so that we can actually not only decode this thing, but actually drive a 7-segment display. So let me talk a little bit about that. So again, our inputs will be 4-bit input, A, B, C, D. Our 1s, our 2s, our 4s, and our 8s. And then the output is a little confusing. I'll use lowercase letters A, B, C, D, E, F, and G. And this is then going to go to our 7-segment display. So something like that. I think that this is this would be segment A. This would be B, C, D, E, F, and G. Okay. And this because well, we can do this a couple different ways. If we're activating here, let me look at the, what do we have in the lab? Yeah. So if we do this, we're going to come over and we're going to go to ground on this, which is common cathode. An alternate way on this, I'm not going to draw the whole thing, but would we, if we were to activate with a low, on this, and then you're going to have to go to what, +5 volts. Okay. So the this is a 7447, whereas this I think is the one we're going to use in the lab. I believe it's 7448. Yeah. Okay. So, and there's advantages or disadvantages presumably to using either one. But we'll be using the common cathode in lab. So that makes it a little easier. I mean, I don't think anyone was too thrilled about trying to do arithmetic with a calculator that just lit an LED that was LED number 5, right? Okay, that's not particularly useful. But when we start seeing something like that, we can probably deal with that. There's a few other things on the 7-segment display. Usually there's a decimal point that you have to deal with. And I think the ones that we will be using in lab, there's 2 connections. Okay, and that's on the back of that handout that I gave you for lab. One thing that students will sometimes try and do is they usually we're somewhere about 150 ohms here. Usually want some protection for the LED. You might say, well, I didn't use protection in the lab for the LEDs last week while they were inside there. You notice the LED, it was built in inside that when you connected to it. A lot of times students, they don't want to have to go and get 7 resistors, so they'll try and shortcut this process. And I mean, 150 is not, somewhere between 100 and 200, you're probably going to be okay. But what they'll do is they'll take these things out and then they'll put a resistor there. I'll say, okay, it's in series. What's the problem with that? Well, if you have 1 segment on, it's going to be really what? Really bright. If you have 7 segments, you're going to have, I guess maybe there's no use of 1. So I guess I'd have to say if you have the 1 on as in 1, be really bright, won't it? Okay? So it'll look something like this, and you'll be burning up your LEDs. Whereas if you have an 8, going to be very faint, isn't it? Okay? So if you want a consistent brightness of the individual segments, this is the way to go. You put the resistors in there. It's not that big a deal. They punch right into the boards. So, questions with that? So don't do this. I think that gets us to a pretty good stopping point. Used to be in the past we would go in and start to look at binary, not a stopping point for today, but a stopping point for digital. Yeah, we'll probably not go this short, but we used to go on and talk about binary arithmetic, addition, multiplication, and so forth. That takes us then into flip-flops. And once you have flip-flops, you can start to think about building memory and things like that. Well, this is just kind of a little quick overview, so I think this is probably a good spot to bail out of this. So with that, we're going to transition back into the other textbook that we've had for the last couple terms, and looking at analog circuits. So, incidentally, the exam on Wednesday is going to be a strictly digital, okay, 1s and 0s. So, what we're going to cover today what we're going to cover from here on out today will not be on the exam. So, don't want to panic anyone. Well, one of the things we're going to go back to the in the textbook, we're going to look at chapter 14. And we were in chapter 14 last term. That was the work we did with the filters. Remember that we looked at some standard filters like this with a resistor and then the capacitor and then the inductor. Or maybe we looked at the parallel counterpart like this. Okay, and we said that for either one of these, the resonant frequency omega naught would be equal to 1 divided by the square root of LC. Remember that when we did that? Where we had R and C and L. And when we put this onto a filter, if we do a band pass, we could do a variety of different filters, but we could show this on the band pass like this, where we get this output over input. That's our transfer function, and where that goes to that that value, that would be our omega naught. Remember when we did that? Okay, so I'm just going to probably reiterate a few things here. I'm not going to go back and reinvent all of this. This is fairly limited because we worked with a circuit that looked like this or a circuit that looked like that. If you started to rearrange where those were, maybe instead of having parallel, strictly series or strictly parallel, you had a combination of, you had to go back to the drawing board, right? But let me reiterate this. This comes up quite a bit. A couple things that we did is we talked about the bandwidth. So if you, let's say that you had this value of 1 here, if you take 1 over the square root of 2, or whatever that value is over the square root of 2, you get these half power frequencies, omega 1 and omega 2. And we could say that omega 1, or omega low, which it's sometimes described as, is the resonant frequency omega naught, and this is all, of course, in radians per second, times minus 1 over 2q, the quality, we've got to address that, times the square root of 1 over 2q squared plus 1. And then likewise omega 2, or omega high, is equal to the resonant frequency, and is exactly the same thing, except we put a plus there, plus 1 over 2q, plus the square root of 1 over 2q squared plus 1. If you have your notes from last term, it should be exactly the same. Now, we have to talk about the quality. Quality Q, we could define this as omega naught times L over R, or maybe 1 over omega naught times C times R, or 1 over R times the square root of L over C. And we saw those. Your author did a pretty good job of deriving those. This is for series. So all these calculations thus far were the same for series or parallel, but those are all for series. And then if we want to know about parallel, we'd have that the quality would be omega naught times RC, or R over omega naught L, or R times the square root of C over L, and these would all be for parallel. Okay, for parallel. Let's see, the reason we wanted omega 1 and omega 2 is we know that the bandwidth, usually given the symbol beta, bandwidth was equal to omega 2 minus omega 1. Okay. We could also, if we're looking at series and parallel, while we're up here with series, we could say that the bandwidth beta would be equal to R over L, and for parallel, we could say that it was 1 over RC is equal to the bandwidth. So I think hopefully you still have the index card kicking around where I said to put series on one side and parallel on the other side. I'm not going to spend too much more time going into that, but those are kind of useful if you have these very standard circuits come up. And I guess that gives us a starting point to start to look at more complex things. Questions with that? Well, what we're going to be talking about is the Bode plot or the Bode plot. We'll try and deal with even the pronunciation on that in the future. But before we get into that, I want to go back and refresh our mind with some algebra, talking about this transfer function. How do we come up with those transfer functions and things like that? So I'd like to start out with some fairly simple problems and work through those. So let's say that we start out with a problem like this, and I'll put my inductor here and the capacitor here and the resistor here. And we will look into these terminals and talk about the impedance Z. And if I'd like to find the resonance, what Z is at resonance, okay, I can go through this process. Now remember, we did that before on this already, right? I mean, these were, for instance, this one here, we could say that, what was Z on this thing? Z on that was equal to R plus J omega L plus 1 over J omega C, is that right? And we said at resonance, these two, we got those two to cancel out, didn't we? Okay, so this thing really just looked like a resistor at resonance. But what we'd like to do is we'd like to find the, I guess I don't want to find the impedance at resonance. I'd like to find the frequency for resonance. So maybe I'll find omega. Let's modify that a little bit. Okay. I guess we could say that was 0, but that wouldn't be much fun. Now, could we use that omega is equal to omega naught, which is 1 over the square root of LC? Does that sound good? It's a trick problem. Is that easy? No, this is only good for what? If you have something like this, where you have the resistor and the capacitor and the inductor all in series, or you have the resistor, the capacitor, and the inductor all in parallel. Is that what we have here? No. So we can't use that. So we're going to have to go back and see if we can derive it. So let's derive this. Let's talk first about the impedance. So I could talk about the impedance Z. I could say that that's what? The two branches in parallel. So I could say that was R plus the impedance of the capacitor in parallel with the impedance for the inductor. Which if I put that into math terms, I would have the resistance R minus J over omega C times, let's see, product over sum. I'd have J omega L divided by R minus J over omega C plus J omega L, right? You product over sum when you have two things in parallel. So our symbol for parallel here. Okay, well, let's see where that ends up now. I could multiply that through, so I get R J times R times omega L minus, when I multiply that, I get to cancel the omegas, and I have minus J squared. The omegas cancel, and I have L over C. Is that right? And I could divide this by R plus J. Factoring that out, I'd have omega L minus 1 over omega C. So far, so good. What is J squared? J squared is minus 1, is that right? Because if I take the square root of both sides, J is equal to the square root of minus 1, isn't it? Yeah, okay. So if I have a negative sign there and I say J squared is minus 1, those cancel, so I could say then that the impedance, as I continue working through this thing, is equal to, let's see, L over C, because the negatives will cancel. I have L over C, and then I will have plus J omega RL, divided by R plus J omega L minus 1 over omega C. Let's see, could I do that a little differently? I think I could get the factor in L out. So I'll say that I have L times 1 over C plus J omega R divided by R plus J omega L minus 1 over omega C. So that's not bad. That's our expression for Z. What if I want to talk about the angle of Z at resonance? What's the angle of Z at resonance going to be? I mean, before, when we look back at this one and we talked about coming up with this, I think we did do the derivation on that. We didn't do too many derivations, but I did derive that. We said that these two would cancel each other out, right? And this thing would look resistive. What's the angle on something that is resistive? Yeah. So it's 0 degrees, isn't it? So I know then if the angle of the impedance is to be 0 degrees, that is the angle of the numerator, it better be equal to the angle of the denominator. So if I look at the angle of the numerator, I could say the angle here is equal to the arctangent of what? Omega R divided by 1 over C, right? And what's the angle here? It's going to be the arctangent of omega L minus 1 over omega C divided by R. So if we said that the angle of Z is to be 0, wouldn't we be able to say that these two angles would equal each other? So we could say that the arctan of omega R over 1 over C is equal to the arctan of omega L minus 1 over omega C over R. What's the first thing you want to do when someone gives you something like that? I'd probably take the tangent of it, right? Yeah, so if you take the tangent, you get that omega times R over 1 over C is equal to omega L minus 1 over omega C divided by R. So far, so good?
You explain how you use the algebra side of the
Oh, okay. So I don't think so. Let's see. So the question is, how did I get from this, I mean, L is just a real number there, right? The way we got that factored out. So this is, it's just a constant, a real number, times a factor here. Okay? And if I look at this factor in terms of complex number, this 1 over C plus J omega R, we could really write that, I mean, if we were in math class, we'd tidy this all up and sanitize it and say this is A plus JB, right? Okay, I mean, if we were in math class, we'd use I rather than J, but we'll stick with J. So if I go into the real and the complex plane, so there's the real. And then here's the imaginary, and I spell imaginary weird with a J. Okay, so there's imaginary. So I go over here, A, that's the real part. I go up B, because that's the imaginary. And it could be in any quadrant, but I'm just keeping it easy in the first quadrant. So we're representing this point here, and we're looking for that angle. So what's that angle going to be? The arctan of the opposite side, which is always the complex portion, that being B, divided by the real portion, A. So if I make an extension, what could we say that this was? Omega R divided by 1 over C. Good with that? And this is why we're going back and talking about that before we just get into the Bode plots and figure that this is all second nature. We haven't done this all that much, and it's been a few weeks since we've done this. So I want to go back and make sure that we're comfortable with this. So if we go back and we pick up at this point right here, let's see what we've got then. So we could say that omega R 1 over C, and I'm just rewriting that, is equal to omega L minus 1 over omega C divided by R. So what's a good plan on that? Multiply both things by R. So I'm going to have omega times R squared, and that C that's in the denominator of a denominator is really in the numerator, doesn't even know it, is equal to omega times L minus 1 over omega times C, right? So probably a good plan to multiply everything by omega, right? So I'll have omega squared So I have omega squared times r squared times c squared, because I've decided to multiply everything by what? Omega c. So then I'm going to have omega squared LC and then minus 1. I could move this over here, so I'd get omega squared r squared c squared minus omega squared LC is equal to minus 1. So I could factor this out, and I'd say that omega squared times a LC minus r squared c squared is equal to 1. So I switched the negative sign on the left so I could get rid of the negative on the right. So solve for omega, and we would have 1 divided by the square root of what? LC minus r squared c squared. And I should really, since this is resonant frequency, this isn't just any frequency, this is resonant frequency, I probably should call this omega naught, because remember we're solving for the resonant frequency. So we'd have something like this, which is certainly not 1 over the square root of LC, a little more complicated than that. Okay with that? So we do a lot of algebra in here. We multiply, essentially multiply both sides by the same thing. Sometimes I'll multiply, have I done it up here? We'll do it sooner or later. We'll multiply by weird looking ones where the numerator and the denominator will be this odd term, but it'll be the same. So we're effectively multiplying by 1. Well, let's try another example. This one might be a little more recognizable. So we'll go back here to an inductor, a capacitor, and a resistor. And we'll talk about having some Vn across here. And maybe take our output here. So this is L, C, and R. And we'll talk about this output here. And I would like to come up with the expression for the magnitude of V out divided by V in. Okay? So I want to find the ratio of the output over the input, and then I want to find the magnitude of that. When I go to plot the graph, I mean, that's what I have here. This is this piece right here. Then we have the frequency there, and we could get some nice bandpass filter out of it if we wanted to. Okay. Well, let's see. How can I do this? Simple voltage division, right? Where we could say that V out would be equal to V in times the impedance across that has the output taken across it, so that's just R, divided by the total impedance. R plus J will have omega L minus 1 over omega C, right? So then we could say that V out over V in would be equal to R divided by R plus J omega L minus 1 over omega C. Getting so close I can taste it, right? Yeah. I mean, we could take it at this if we wanted to and find the magnitude. Maybe I will do that. What's the magnitude at the top? What's the magnitude of R? What's the magnitude of 1? 1? Okay, so the magnitude of R is R. There we go. Thank you. Okay, so we've got R divided by, and then this is a little more complicated because if I go to the real and the complex plane, R is, so there's our real and there's the imaginary. R is just out there, so its magnitude is very easy. When I then look at this term here, this omega L minus 1 over omega C and R, I'm going to have to go over R, and then I'm going to go, when we'll assume this is a positive number, it wouldn't need to be, but we'll have omega L minus 1 over omega C. So the magnitude of that is this distance here, isn't it? How do I get that? Pythagorean theorem, absolutely. So I'll have R squared plus omega L minus 1 over omega C squared. Okay? Now, someone might come along and say, I really don't like that R in there. I've got an R here and I've got an R there, so I think I could do better. So I'm just going to put an OR here. There's nothing wrong with the work that we did, but maybe you'll see someone write this as 1 divided by 1 plus J times omega C over R minus 1 over R omega C. Is that possible? Yeah. Multiply both terms in the denominator by R, multiply both sides in the numerator by R. So if you take this thing and you multiply this, if you multiply it by R over R, you get exactly what we started with. So then the magnitude here would be 1 divided by the square root of 1 plus omega, was it omega C? No, this should be, I should have omega L. This is omega L, isn't it? Yes, omega L over R minus 1 over R omega C. Okay, and if you're stranded on a desert island without a calculator or something, this is probably a little easier form to recognize what's going on. Yes?
Shouldn't that, when the J gets squared, shouldn't that negative sign make a difference?
I'm not squaring the J, I'm just putting it on the plane here and finding the length of the diagonal. Okay?
So
So, yes?
the
Well, I'm not trying to say that the denominator is Vn. I just divided both sides by Vn. So I got rid of the Vn. So, I mean, essentially on this, I multiplied by both sides by 1 over Vn, right? That's how I got to that.
Well, then just the denominator in that next.
Here?
Yeah.
Okay.
So that is just the hypotenuse of that triangle.
Absolutely. Yep. Because the complex side is right here. That's that side. And the real side is right there. And just like on the previous problem, if I wanted this angle there, what's that angle? Arctangent of omega L minus 1 over omega C divided by R, right? I guess that's kind of an FYI. Didn't necessarily need that, but it was fun. So if you take either one of these and you could plot this. So what I've got here then is this, okay? And you'll find this if you go to the website. So website, and there's some folders at the bottom. Transfer function folder. There's a folder at the bottom of the 203 page, has transfer functions in it. And this is actually just an Excel file. The name on this would be filter.xlsx. So there's several MATLAB files in there. This is one of the few Excel ones. And some of you may recognize this from good old GE 101, right? Not GE 101, GE 103. We're using Excel. So we start out with our frequency f. We convert that to radians per second. And then I have the two transfer functions. That's leaving the resistor in the numerator. Here is getting the resistance out of the numerator. And you'll see that it comes up with exactly the same values. That should not surprise anyone. But when you plot that, you can get that it looks like what kind of filter? Bandpass filter, right? Okay. And once you get something built like this, the really cool thing is if you start messing around with the resistance, if you increase the resistance, it's going to start to open up the bandwidth, which is going to be a problem. Particularly 10 ohms. Does that seem like a realistic resistance? Now we're going to be building filters later in here, and when we go down there, we're going to find that the resistance in the inductor is usually pretty significant. There'll be some RL that causes problems. Our source, what was our source down in the lab? I think we had 50 ohms in that thing, so it may not be very realistic to have 10 ohms there. So start putting 100 or 1,000 there and seeing what you get, and the filter is going to change quite a bit. Okay. So we're going to be doing a lot of this throughout the term, coming up with these transfer functions and using them to model the circuit. Questions with that? Well, let's try one more. I guess I'll submit this as page number 8. So let's say someone gives us a filter like this. Definitely nothing we've seen before. It doesn't fit into that nice parallel or a series model like we have. And we're going to take our output across the resistor. And well, I guess we better call that R2 because we've got two resistors. We'll call this R1 and we'll call this C, and we'll say that this is then across here Vn. Okay. So what we'd like to do is we'd like to come up with what kind of a filter is it? band pass, low pass, high pass. Okay. I guess we got a basically a let's see, we'd have band pass. Oh, I guess with a notch we only have a 1 in 4 chance. So hopefully with some calculations we can do better than that. So if I look at V out over VI, our transfer function, is going to be V out over Vn. Okay. And that would be equal to the transfer function. So that's our test. Well, let me see if I can come up with an expression for V out. What's that going to be? Well, that's really just our Vn, voltage division like we did in the last problem. We take the total voltage, we multiply by R2, and then divide by what? R2 plus, we could call this, for a simplified sense here, let's just call that Z, okay? Is that fair enough? If I took the impedance of these two that are in parallel and added it to R2, that would be our total impedance, and we should be good. So we can say then that V out over V in is going to be equal to R2 divided by R2 plus whatever the impedance of that parallel branch is. Well, let's keep at this then. So I'm going to have that V out over V in is equal to R2 divided by R2 plus, let's see, what do we get for that? Product over sum, right? So Z would be equal to R1 times 1 over j omega c divided by R1 plus 1 over j omega c. Is that right? Yes. Because the j's in the denominator, they should be positive, shouldn't they? Okay. So let's see. How do I want this to look? Why don't I multiply the, I'd like to multiply this z. I'll just work on this z over here for a little bit. I'd like to multiply it by j omega c over j omega c. Is that fair? Yeah, I mean, I'm just multiplying by 1. It's a weird looking 1, but it is 1. So when I do that, I get to, say, j omega c. I have R1 in the numerator, and then I am dividing by what? J omega c, I will have 1 plus j omega c times R1. Well, that tidied that up a little bit, didn't it? So why don't I put that right here? I'll bring that over and I will say that I have R1 divided by 1 plus j omega c times R1. Now what do we do? Probably get a common denominator, right? So I could addition in the denominator. Oh, here?
Then move to the numerator of your V out over V in. You move it over. So you have plus R1 over.
Well, this is Z. Yeah, I still got the R2. If R2 wasn't there, yeah, then I could just flip that, and life would be good. But I'm gonna eventually I will get there, but I'm gonna have to get common denominator. So I'm gonna have this R2, and then I want to multiply. To get a common denominator, I'm going to multiply R2 times this thing. So I'm going to have R2 plus J omega C R1 R2 plus R1, and then it's all divided by 1 plus J omega C R1. So then I can flip that up there, and I'm going to have R2, because I'm going to multiply R2 by this term down here, so I'm going to have R2 plus J omega C R1 R2 divided by, what do I get, R1 plus R2 plus J omega C R1 R2. What would be a good plan at that point? Give up? No, I think we're ways from there. I'm going to multiply by a really weird looking 1. I'm going to say 1 divided by R1 R2 times C, and then I'm going to have to do it on the bottom denominator. So this is my numerator, and I'll then have 1 divided by R1 R2 and C. So when I do that, I come up with, let's see, I get rid of that, and that. So I have J omega plus, get to cancel the R2's, and I have 1 over R1 times C. That's the numerator. What do I get in the denominator? I'm going to have J omega. And then I'm going to have what? Plus R1 plus R2. I guess I could leave it like that. Divided by R1, R2. And this would then be, have a C in it. Is that going to be right? Yeah, that should be fine. So put a C in there. Yeah, I think that's good. Now I think when I did the simplification, I did one more step. We'll try this on. We could have J omega 1 over R1 times C, nothing new in the numerator, but the denominator, I could say that I have J omega plus 1 over, and then I could take R1, R2 divided by R1 plus R2 times C, which is kind of nice because then I have these two terms here. And if I wanted to look at this without a computer, it's kind of nice. I have exactly the same in the numerator and denominator, except where I have R1 here. What do I have? R1 times R2 divided by R1 plus R2. So we could play around with that if you wanted to. I actually put this into, so we've got page 9 here. I put this into a, and this is again if you go to the website, and this is under transfer functions. And this is a function plot 1. Okay, there's about 3 of them in there, but function plot 1. And I put this in here. You can see the numerator. There's the numerator. There's the denominator. I find the ratio between them and I plot them on a log plot. This is going back to what, MATLAB? If you don't have MATLAB, you got it in the computer lab or a good one. And I've got some files on there also in FreeMat. Okay, so a couple options for you. So you can go and look at that code probably in a little more detail. When you come up with this plot, you get something like this. So what do you think that is? If you put something in at low frequency, you don't get much out. You put something in at high frequency, what happens? You get almost all back out, don't you? So what would you call this thing? High pass filter, right? Okay, high pass filter. Yeah, low pass would be just the opposite. Like that. Probably can't see through there. So, high pass filter. So coming up with these transfer functions, I'll call this page number 11, coming up with these transfer functions, and you've got access to the website and probably a little better way to look at those. But coming up with the transfer functions is important because then you can go and plot them and learn what you have going on. Okay. So next time we get together, we'll do the examination. So a week from today, when we get back together in lecture, we'll continue on with this. I think this is good practice, getting back into the swing of these, coming up with these transfer functions, and this is then going to lead into what else can we do with the transfer function, and that's coming up with the Bode plot. So that's where we'll go. Take care till then.